Hello and welcome to CodeRage 6. My name is Bojan Mitov, and in this session we'll demonstrate implementing video audio processing, digital signal processing, artificial intelligence, and computer vision with FireMonkey. Mitov software offers a variety of products for video processing, audio processing, digital signal processing, computer vision, and artificial intelligence. We also offer some low-cost solutions such as basic video and basic audio for only basic video and audio capturing, processing, and playback functionalities. We also offer data visualization products such as PlotLab and InstrumentLab. Our current products support VCL, and in this session we'll demonstrate our current pre-release port to FireMonkey. We'll start with an empty FireMonkey application. We'll add AVI player component and image display. We'll connect the output of the AVI player with the input pin of the image display using the brand new and completely redesigned OpenWire editor. Then we'll select File to Play. Our first video player application in FireMonkey is working. Let's do some video processing. We'll start by adding a grayscale component. And image display for it. In the editor, we'll connect the video to the grayscale component and the output of the grayscale component into the image display, and we'll rearrange the components. We have our first video processing application. It is still boring, so we'll add some geometric transformations. We'll use rotate and image display to show the rotated video. We'll connect the grayscale video into the rotate and the rotate into the final image display, and we will put angle of rotation 30 degrees. Here is our rotated video. If we want to rotate the original video instead, we can connect the rotate to the original video and rearrange the filters. Here is our original video rotated. Next, we'll demonstrate how we can combine video. We can add combine component, and we'll combine the original video with the rotated video. And we'll put the output in image display 3. Here is our combined video. Next, we'll add some video analysis. We'll add a scope component, a histogram component, we will add 2 more channels into the scope component. We'll connect the scope component to the histogram and the histogram to our original video. Since the original video has less black color, it will be more interesting histogram. And we have live RGB histogram in our FireMonkey application. Next, we'll add audio display to show the audio from our video. We'll add a scope component and we'll connect it to the AVI player. Here is our audio. Let's do a little more with the audio. To free some space, I'll remove the histogram display and the original image display component. And I will add a waterfall component. I will also add a spectrum component. And I will connect the spectrum into the waterfall and the input of the spectrum into the audio of the video. After arranging the components, if we run the application, you can see the spectrum of the audio over time displayed in the waterfall component. Next, we'll add some instruments to show how our video progresses. We'll connect those three instruments to the progress of the video. The only thing left to do is to change the source of the time in the clock. We'll change it to value, run the application, and we can see the progress of our video in various instruments. Those instruments can also be composite components. In this case, I will modify the gauge to contain internal segment gauge element. We can also add internal thermometer and even internal clock. We'll change the position of the clock and run the application. As you can see, all of the displays are working as one composite display. Our controls integrate well in the FireMonkey framework, and we can even add effects. Our components are still operational. We can even add image display inside our angular gauge. And we can make the image display big enough to take over the whole gauge. The only thing we need to do is to connect with the video. we have video inside our gauge. We can not only add video inside the gauge, we can also add gauge inside the video. For this, we'll add a new component called TVO Draw, image display for it. We will connect them using the original video as source. Then we'll add a layer inside the draw component. In this case, we'll add angular gauge and we'll connect our angular gauge to the progress. Here is our gauge rendered inside the video. We can even add some effects, such as fire. And we can set the effect to be applied to the angular gauge. Our angular gauge now is on fire inside the video. Finally, we can record our processed video. And we can even broadcast it over internet. We add a logger and broadcast component, connect them with the video containing the gauge on fire, select file name to record, select profile for our video broadcast, and we should be good to go. Our video is broadcasting. We have to allow that on the firewall. And now we can connect to our video over the internet, and we can also play the recorded file. Here is our recorded file. You can see that it plays in Windows Media Player and the video is recorded with the gauge and the fire effect in it. We can also display our video inside a matrix component from Instrument Lab. For that, I will free some space on the screen and we'll drop matrix display. Then in our matrix display, we will add external image display matrix layer. And we will connect it to our processed video. Then we will rearrange the open wire diagram. Let's run the video. You can see the processed video being played inside our LED matrix component. Finally, we will add ppm meters to our application to show how the audio changes over time. We'll connect the audio output pin to the ppm meter and the output of the ppm meter to our angular gauge to show the ppm values. We can even allow the audio to be heard while the video is playing. Again, we'll connect the audio output pin of the video to the audio out component. Here is our application playing again, and we can see the ppm meter.
Peaceful life on an all-new episode.
Now we'll create digital signal processing application in FireMonkey. We will start by adding a random generator. Then we'll add scope component. And we will connect them. We can see the random noise inside the scope component. Let's add some signal processing. We'll add low pass filter. We will connect it to the random generator. We will add one more channel to the scope. And we'll connect the low pass filter to this channel of the scope. Here is our filtered signal. Finally, we'll add Fourier Transformation. And we'll display it in waterfall. We'll reduce the order of the Fourier to see it more clear in this small screen. We'll connect the signal to the Fourier transformation and the spectrum to the waterfall. Here is our original random noise in the waterfall. Now we will connect it to the filtered signal. Here is the Fourier transformation of our filtered signal. You can see that we have only low frequencies. Let's show how we can make Lissajous figures with Signal Lab. We'll add two signal generators. We will change the frequency of one of the signal generators. Then we'll add scope component. We will connect one of the signal generators to the Y input pin of the scope and the other to the X input pin of the scope. We will run the application. Creating Lissajous figures is always fun. Now we'll cover some artificial intelligence with Intelligence Lab. Before we go, we first have to understand what we can do with artificial intelligence. We can implement spam filters, we can implement computer vision, OCR, speech recognition. We can develop diagnostic utilities, industrial control, investment tools for automatic trading, code formatting, automatic code formatting obviously, gesture recognition. We can implement functionality for robotics, games, and we can do even common tasks such as function approximation. Obviously, all of those tasks are becoming more and more important, especially now with the introduction of iPhone 4S, which emphasizes exclusively on the new artificial intelligence functionality. Here are some basic concepts of how artificial intelligence classifier works. First, you have some data. We extract features from that data. In case of example of image, we can use simple features as the grayscale of a pixel, and each pixel is one individual feature. Then the features are fed into a classifier. The classifier is trained with number of images by feeding features into it to recognize the images. And finally, we can start providing real data and having the classifier use its training to recognize the data. The data is recognized into different categories, conditions, or IDs. Variety of naming conventions are used for those. Now let's switch to Delphi and see how easy it is to do all of this with Intelligence Lab. Due to the time constraints for the session, we will demonstrate the artificial intelligence in VCL with our existing demos. However, all of this functionality is fully available in FireMonkey. We'll start with facial recognition application. First, we'll train classifier to recognize between different faces, and then we will use test faces to test the recognition. We have 5 errors over 40 faces, or 87.5% correct recognition. Let's take a look at our code. When we click the train button, we'll create buffer that will contain our training features. We'll populate that buffer with pixels from the grayscale images, and then we will train our classifier with the buffer also providing the ID of the person we are training for. Inside the recognize button click, we again will create buffer containing the features for the recognition. We'll populate the buffer with the pixels from the image we're trying to recognize, and then we'll call predict on our classifier. The classifier on result event will show inside the result the number of recognition candidates, and we'll use the most likely candidate to be displayed on the screen. We will also display the calculated distance between the facial image and the training, and we'll check for errors. We will not dig further into the code due to the time limitation, but this demo, as all of the rest of the demos, are included in the installation of Intelligence Lab. Now we will show quickly the rest of the demos included in the install. This is a self-organizing map demo. We'll train the self-organizing map. We will provide groups of data. The self-organizing map will automatically organize them in different categories. Then we will test a single prediction. This is naive-based classifier. We have trained it with data in 3 different categories represented by those small colored circles, and then we have classified each pixel inside this T image into the corresponding category. Here is a similar KNN demo. And neural network demo. We can train the neural network with backpropagation or resilient propagation. In this demo, we train and classify only in 2 categories. Here are the two training components which we can use to train the neural network. Now we'll make a quick demonstration of some of our computer vision components. This demonstrates extracting canny contours. This demonstrates finding whole lines and segments. Demo finding circles in the image. Demo finding and extracting contours. We can also find the bounding rectangles of those contours. Demo finding and tracking targets. This demonstrates finding faces inside video. This demo shows extracting robust features inside the video. Demo finding people inside video or image. This demo actively learns and subtracts the background from the video. As you can see, the longer we play, the better it learns to subtract the background. This demo finds known contours inside the image or video. This demo demonstrates all of the functionalities in a single demo, which uses layers to render the extracted data so your application can have 0 lines of code. Here is the code for this particular demo. As you can see, there are 0 lines of code. It is done completely with open-wire connections. And here is the open-wire diagram. We will show a few more demos from Video Lab to cover some areas we did not cover in our demonstration. Here is a video filters demo. A more advanced video combine demo between two different videos, one of them being rotated. Here is also the open wire diagram for this demo. It is fun to just drop components and connect open wire pins. However, sometimes we want to process the video inside our code. The generic filter allows us to do that. Here is a demo showing how we can process video inside our code. And here are some examples how we can loop through all of the pixels and process the video using different mechanisms. Let's see the demo. Here is custom processing inside our code. Sometimes we want to capture bitmap from the video. Here is a demo showing that. Here is how, in generic filter, we can convert the video buffer into a bitmap. Sometimes we want to process simple bitmap instead of video. Here is how we can do that. We simply call the filter with two bitmaps and the image will be processed. we can have transparent colors inside video or image. We can use the free open source free-frame plugins to process our video. We can compress and transmit video over internet. We can do our own painting over the video. Here is how it can be done inside code. We can have vector scope of the video. We have a number of remapping filters, including swirl effects, fisheye, and more. We can render text in the video. We can have water effects or fire effects. And we can even set the text specifically on fire. Now we'll demonstrate some of the Audio Lab functionalities. Here is audio processing demo showing the usage of the graphic equalizer. Here is audio recording demo. As you can see, I am recording myself right at the moment. We can also generate audio. We can mix different audio sources. We can perform custom filtering over the audio the same way as we showed in VideoLab. Here is a custom filter. We can compress and transmit audio. We can implement ppm, VU, and RMS meters over the audio. We can load and plot entire WAV file, and we can play it.
And evil reunite.
As you can see, we can even seek in the audio. This concludes our session. Thank you for listening. My name again is Bojan Mitov, the president of Mitov Software. You can see my email on the screen. Our website is at www.mitov.com. We have already demonstrated our products. In addition to them, we support a number of open source libraries, including the OpenWire library, which you have seen being used in all of our components. It is available at www.openwire.org. We also support the open source IGDI Plus library, which is used for all of our instrument lab components and is available at www.igdiplus.org. We also offer 25% discount to the participants of CodeRage 6. You can use the coupon on the screen, and the coupon will be available until the 25th this month. Now it's time for questions and answers.